shows now how the decay is happening. Because now if this sigma is negative, it will be decaying function. If it is positive, it will be an increasing function. So if we have now allele, so this was, so the one I have just illustrated is the one that actually comes light here. Well, let's first of all deal with the real exponential signal. When we are dealing with the real exponential signal, we are saying that the complex part, this one, is 0. Of course, I repeat that x of t is defined as e of s of t, and we are saying s is a complex number, so we are going to have e sigma plus j omega t, and you break that down. Now, before you even break down, if you consider the complex part is 0, then you are going to have e sigma of t, and meaning this becomes purely real exponential value. And that is the, so this is the one that gives us an increasing exponential function. And we are saying that if the sigma is less than 0, meaning it is negative, then we have the decaying function as illustrated there. So those are the two ways in which you can have an exponential function, either it is increasing or decreasing. But then if it is not purely real, but it is complex, then you see that it takes the shape that these two have taken. It has the periodic part that is defined by the sine and cosine, but then there is also the effect of decay or increase as illustrated by these curves that are either increasing or decreasing. So I think that serves to illustrate the two important points about the complex exponential signals and real exponential signals. And I guess with that, we have seen how they can be plotted. And we can move on to the sinusoidal signals. And of course, you are very conversant with the sinusoidal signals. And sinusoidal signal is always the one that might have a sine, or sine of omega t, or plus some theta, or cosine of omega t plus some theta. That is a general definition or illustration of sinusoidal signal. And we are saying that it can be expressed as having an amplitude there. And therefore you say that becomes your x of t, and we call that your sinusoidal signal. So the A is the amplitude of the signal. This is the radian frequency, and this is the phase, of the phase shift of your signal. And of course, we are saying that this term here and this term here are expressed in radians. But of course, omega is expressed as in radians over time. But then when you multiply omega with t, and or with t there, then of course time goes, and you end up with these two terms defined in terms of radians. And of course, we can see that a sinusoidal signal is periodic, and the fundamental period is defined as we said earlier, t naught over 2 pi, t naught is equal to 2 pi over omega. And you say that we generally know that, that omega is equal to 2 pi f naught, and therefore we can always say that the fundamental period can be expressed as the 1 over frequency or fundamental frequency, as you can see in question 138. And of course, from that you can get the reciprocal of this and the reciprocal of this. You'll get the fundamental frequency F naught, which is expressed in hertz. And I have already alluded to this definition, which I believe you are conversant about. And the omega naught is normally referred to as the fundamental angular frequency, which is expressed in radians. Again, it's very important. So we are saying further that from the Euler's formula that we have already expressed, this equation on 141 or equation 137, which is what we had right here, can be expressed from the Euler's formula in terms of an exponent. And if you remember what the Euler's formula said, just for the sake of definition, we said that E j theta is equals to cos of theta plus j sine theta. And you can see that this is the real part, this is the imaginary part. So since we are working now with the cosine, we can say that cosine of theta is the real part of this function E j of theta. And that is how we transverse or convert from equation 137 that we had the A cos omega naught t plus theta, and now we are expressing it as the real part of the of our exponent value. And of course, now my theta was defined as omega naught t plus theta. So of course, this takes the form without much ado. I think that is clear. I hope my screen is still visible, and I have zoomed a bit for the sake of this bit that may not be very clear. Of course, for in case you don't know, the real part is expressed as R3, and the imaginary part is expressed as IM. So you can still express the sine part using the imaginary part of the exponent value, which is defined as 140. And for those who are not very conversant with the concept of the period, then the fundamental period is defined as the distance between the two peaks of a periodic signal. So that is how you define your period as T naught. So that serves to define I guess we have dealt with 4 items. The exponential signals, exponential signals, then complex exponential. Actually, we have dealt, I think, with 5. Complex exponential, what am I saying? We have dealt with the exponential signals, complex exponential signals, and we have also dealt with the sinusoidal signals. And of course, earlier on, we dealt with the unit step, or the unit impulse and the unit step. So all these were in continuous time. They are in continuous time. So they are continuous time signals. So that serves as for the continuous time. And now we jump to the discrete time. And in discrete time, we are still going to deal with the same kind of signals. And you're going to start with the unit step again. And now we are saying the major difference, we are dealing with sequences, which are expressed now as UN. That is, the UN is an integer, or the N is an integer. And therefore, when you say UN, you're expressing the unit step function. In unit step function in discrete time. Again, remember how we express in the continuous time? This is the same unit step function, but in continuous time. So what we are now saying that, Ed, I would want you to notice very carefully here is that for the discrete time, we have the u of n is defined at n is equals to 0. It is defined at n is equal to 0. But we said in the continuous time that u of t is not defined at t is equals to 0. So that is a major difference that you need to observe, particularly with the unit step function. And we are saying, of course, that the u of n will be 1 when n is equals to or greater than 0, and it will be 0 for n is less than 0. And figure 110b illustrates that concept, that as long as we are in the positive n, and n is representing time, then we are going to have unit values 1, 1, 2, 3. Of course, 1, 1, 1, 1 for any value of n that is bigger than 0. And for shifted, this is the one we call shifted in time, unit step function. Of course, in discrete time. We are simply saying that instead of having the first value at 0, as we had here, this function has the first non-zero term at k. And we are saying that it is defined as u of n minus k is equals to 1 when n is bigger than or equals to k. That is, I guess, very important. So the k is the starting bit. If you can actually see that if it is not shifted, that means my k is equals to 0. Therefore, when it is equal to 0, that means the starting point will be 0. But if it is not equal to 0, that means the first value that is non-zero will be at k value of time. So of course, always remember that n is representing time in discrete time. That is the symbol that we use to represent that. So this is the unit step function in the unit step function in discrete time. And this other one is the unit step function that is shifted with k values of time. And of course, we jump now to unit impulse sequence. And as we define the unit impulse sequence, and this is now, I think, the bit that you need to be very clear about. We said, and that is the clarity I want to make, that d of t is equals to infinity. Because it is not defined as t is equals to 0. But the major difference with that is that d of n, which is in discrete time, is equals to 1. Because at t is equals to 0, delta of t is defined. So that is the major item that you must observe, particularly with the difference between the unit impulse sequence in time and in continuous time vis-a-vis the unit impulse sequence or the unit impulse function in continuous time. So of course, this is the definition, that it will be 0 for n is not equal to 0, and for n is not equals to when n is equal to 0, then our function has a 0 value. And this is how it looks like. Figure 1.1b, that our unit impulse sequence will have a 1 value at time is equals to 0, but everywhere else it will have 0 values. But when it is shifted in time, which is k units, then we are saying that at the k unit, that is when our impulse unit impulse sequence will have a non-zero value. And I'm giving this example again and again. If k is equals to 0, that means this unit impulse sequence is not shifted. Therefore, the value the value will be k is equal to 0. It will actually move there. So I guess that is quite clear and well illustrated for both the unit impulse sequence and the shifted unit impulse sequence. Of course, we are observing that unlike the continuous unit impulse function, d of t, d of n is defined without mathematical complication or difficulty, as we met when we were discussing the continuous time unit impulse function. Now, we can now have some other addition of some more definitions. Now we are introducing x of n, another function that is arbitrary, but is defined, or it is continuous in time. Not continuous in time, but it is discrete in time. And therefore, we are saying, similarly like what we said in continuous time, we had said that x of t times delta of t was given by x of 0 times delta of t. And this is how we did it. We said it in the continuous time. But now we are saying that in the discrete time, if you have x of n delta of n, then it will be equivalent to the value of x, the function of x at time 0, and multiplied by the delta function at n. And we know, of course, for a fact that this is always defined that delta of n is always equals to 1 when n is equals to 0, and 0 when n is not equals to 0. So again, they're saying like we are evaluating this value at n is equal to 0. And I hope that makes sense. So if I will do that quick illustration, assume we have, this is my x of n. It is having values like that. And of course, at that point, this is n. So we are asking ourselves, what is x of n delta of n? And we are saying this will be equals to x of 0. So x at 0 is, this might be 5, 3, 2, 6, 6. So we can see that this function is saying that x of 0 is equals to what? Equals to 5. And then, oh, I said here, delta of n. And we know that delta of n will only be 1 at n is equals to 0. So since n is equals to 0 here, 1, 2, 3, 4, we know n is equals to, this will be 1. So we're saying that this value will always be, it's giving us that x of n d of n is equals to 5. That is the meaning of that expression 1, 4, 7. Of course, Vero is asking a good question. Why do we use minus instead of plus? That's a very good question, Vero, and we just know, and of course we'll see it in time, that when we are expressing a positive shift, we use negative. Minus k. If k is equals to, let's say k is equals to 2. Of course, I'm responding to Vero's question that is asking why are we using a minus sign to illustrate a shift towards the right. And I know that is what Vero is trying to ask. So assume k is equals to 2. We are saying that we want to evaluate k, a value of x of the function of n at k is equals to 2, we are going to find that when n is equals to 2, when n is equals to 2, that is when we will have x of 2 minus 2. And that will become equals to 0. No, not equals to 0. Will become equals to x of 0. Now there's something that says that x of 0 at that point will be equals to 5. So here's the point, and I want to make that clear. Probably I should just move to a cleaner page so that we can illustrate that much more clearly. Let me wrap this. Not wrapping actually. Let me add some space here. I've messed up all more than more. I want to illustrate for that point, which is a very important point. I'm creating some space down here for the sake of illustration. And I'm saying the following, that assume you want to, okay, I will use delta of n. We see delta of n is only defined as follows, that it is equals to 1 when n is equals to 0. It is equals to 0 when n is not equals to 0. So if you are to draw this curve here, this graph here, you're going to find that my value of 1 will be there, n is equals to 0 here, and it is 0 in where else? So that is the first one. So the other graph that we want to draw, the other graph I want to draw is, okay, let's assume we have drawn that. The other one I want to draw is for x of n, which is defined as 2, 1, 1.5, 3, or 2, 3. So these are my values. N is equals to 0, 1, 2, 3, 4. So we want to ask ourselves, what is the value of n minus 2? The value of n minus 2, we simply is going to be given as follows, that when n is equals to 2, that is when this function is defined. Therefore, we are going to have x of 2 minus 2 becomes 0. It becomes x of 0. So that point when it where was that? Sorry. Before that, just a quick point. I want to get it quite clearly. I'm actually want to use option 147 because I know that is the one that we are defining, or actually 148. X of n, d, and yeah, okay. That was I. So there is that equation 148 that says the following, that x of n minus k times x times delta of n minus k is equals to x of k delta of n minus k. And here is the point. I want to assume that let n to be equals to 2. And we want to observe what we want to find out the value of n at 2. So when n is equals to 2, we are going to find that x of k will be 2 minus k delta. Okay, I'm going to pick this one only because it's going to help us. 2 minus k is equals to x of k delta of n minus 2 minus k. So what we know about this, about delta, it only defines a value when the value in the bracket is equal to 0. I think that is the bit I want to clarify, that this value becomes, it will be 0. Actually, I want to give that. This value will be, this thing will be 0 if 2 minus k is not equals to 0. And we will have a value of x of k if 2 minus k is equal to 0. So what does that mean? That we are only going to get the value of, at n is equal to 2, we are going to find the value when k is equal to 2. So we are only going to say that when we have selected k is equal to 2 here, if this is now 2, this becomes 0. And therefore, we are going to find at 2. So we are going to find that x at 2 will be equal to what? This value. You know, I've moved in quite a number of steps, but now assuming that we had said x of n plus 2 plus k, that would have not taken us here, but it would have taken us on the negative side. Minus 1, minus 2. So in very many words, like I've expressed, we normally depend on this equation because the delta function is only defined when this term inside the bracket is 0. Otherwise, anytime it is not 0, that is the whole term becomes 0. And therefore, that is why I'm saying that this term here gives us a non-zero term, and therefore the whole of this term becomes 0. But when k is equal to 2, the term in the bracket of the delta function becomes 0, and therefore you're able now to define. And of course, when we say delta of n, delta of 0 is equal to 1. So when you multiply here by 1, which is that, we are left with x of k, and that k is actually at 2. Then we are going to determine the value of x at 2 will be equals to this value, which was, I think we had said this is 2, 1, 1.5. So the final answer will be 1.5. But in the event that, assuming that k was negative, then it would, of course, would have taken us on this other side. And we would have got a different value. So in few words, and again, in very many words like I have used, we are trying to say that for shifting, when you are moving towards the right, we use a negative value. When you're using towards the left, we use the positive k. Anyway, I have used many words, but I think we can move on. So we were here, and I think I've even explained equation 148. And the other term, the other bit that is very significant is the following, that you can be able to express the unit step function or unit impulse function using unit step. So this is the delta of n using u of n. And of course, this is how you do it, as shown in equation 149. And the vice versa is also possible. So if you are to get, of course, you know what this means, and you know what this means. And probably we may still use that space that we were using with that example to illustrate something that is quite are similar. I'm just creating some extra space for my screen so that I can do that. So we have said that delta of n can be expressed as u of n minus u of n minus 1. I believe that is what we have said here. Yeah. So this is what we are saying, that this is the unit impulse function, and this is the two versions or two values of unit step that we are using to express that. So if you are to do that, look at this. I think that is not better. I think there's a better way I can draw here. I think I've just remembered that we normally used to draw using this. Yeah. So this is n is equals to 0. This is n is equals to 1. So if you are to express to draw this value, u of n is simply assuming this is my value of 1. Where is this? My screen has crashed. We start it again. It will not have lost anything. Luckily. So if this is the function of n, we can say to express u of n, it will have, and this is my value of 1 at that point. So this would be a 1, a 1, a 1. This is 2. This is 3. This is 1. So this is how but it is 0 anywhere else, minus 1. This is u of n, just like the way I have drawn it. If I draw using a different color, u of n minus 1, we said that it becomes 1 when this term in the bracket becomes 0. So it is only going to have a value of 1 at that term in the bracket being 0. And it's only going to be 0 when n is equals to 1. So when n is equals to 1, that is when you're going to have a positive term here. So we're going to have that. It starts there and goes towards positive. And anytime, even everywhere else, it remains on the left, it remains negative, it remains 0. So if you are now to subtract the earlier version, which had we could have expressed as 1, 1, 1, etc. This is my u of n minus 0 at n is equals to 0, then 1, 1, etc. When you minus that, you are left with what? You are left with only a 1. And this is the one that is expressed as d of n, which is the one you are trying to define by that point. So I've just tried to illustrate how you can express delta of n using the unit step functions, and two of them. And I can see Rimo is saying there's no sound. I guess it's only him who has no sound. Others have sound. So please respond to him and tell him that we have sound, the others. So I want us to, so we have just expressed equation. We have just expressed equation 149 and shown diagrammatically how you can do that. So we can also show how you can get u of n using the unit impulse function. And this is the one I was actually trying to do here at this expression. It is rather very simple. We are saying it is u of n is equal to sum of delta k from minus infinity to n. And here is something I just chose arbitrary. Let my end be